Hi, I'm Junfei Xiao from Johns Hopkins University. Here I'm going to introduce our paper delving into masked autoencoders for multi-labeled thorax disease classification. Well, in the past several years, Transformer has become the most popular model architecture in deep learning, and the emergence of ViT leads the trends in the computer vision area. ViT shows remarkable performance on natural images. However, vanilla ViT always shows inferior performance in the medical domain. Is ViT really poor with medical images like chest X-rays? We think the key to unleash ViT's potential is to pre-train them. One of the most popular pre-training schemes is called Masked Autoencoders, abbreviated as MAE. Its task is to mask random patches of the input image and reconstruct the missing pixels. We adopted it as our pre-training method and explore further on CheXpert. As the domain gap between natural images and CheXpert is huge, customized recipes are needed for MAE pre-training. We find that there are three crucial factors. First of all, a large scale of data is desired, and the model size also needs to be increased when the data scale gets large to avoid the bottleneck. Secondly, 90% is the optimal mask ratio for CheXpert, which is higher than 75% of natural images. We think it is because of the information redundancy issue, as the CheXpert images are very similar. Lastly, the random cropping operation is very important for MAE, and a modest random cropping scale is preferred based on our experiment results. We also did comprehensive experiments on search and optimal fine-tuning recipe for ViTs. We find that layer-wise learning rate decay, random magnitude, and job pass rate are the most important parameters to be tuned. And to summarize, fine-tuning ViTs on CheXpert is sensitive to the layer-wise learning rate decay factor, needs modest data augmentation, and stronger regularization than natural images. Here are some visualizations of the input image and output prediction with different masking ratios ranging from 75% to 90%. It is worth noting that we also implement a DenseNet version of MAE in the UNet framework. It is detailed in our paper and the codes have been released. We found that 90% is the optimal masking ratio for CheXpert images. You can see that ViT could reconstruct the image very well even with very few patches, while DenseNet performs poorly. We evaluate our models on three public datasets. This slide shows the results on classic NIH ChestX-ray dataset. With MAE, the ViT small model achieves comparable performance to SOTA CNN model and shows great scalability on the scale of pre-training data and the model size. For the results on CheXpert, our model also achieves SOTA performance and performs best on the atelectasis and edema diseases. For the COVID-X benchmark, our performance is also competitive to state-of-the-art CNN models. We believe that many researchers in this area desire a comprehensive comparison between CNNs and ViT, so we made a very fair and comprehensive benchmark, including various kinds of state-of-the-art training methods. Here are some attention map visualizations. We found that the classification maps of DenseNet are larger and more focused than ViTs. We think more explanation are needed to explain ViTs. So to summarize, our paper comprehensively explores the MAE pre-training ViTs on CheXpert images and reveal the huge potential of ViTs. We also provide a fair and comprehensive benchmark to compare ViTs with CNNs. All the code and models are publicly available. Please feel free to play with them. Thank you.